As we move on, I promise you this problem will be a little bit easier than the previous ones because you're not going to make an equation. You are just going to be comparing an equation and a graph. So that's going to be nice. We're going to move on, make it a little more simple. All right. Remember, when asked to compare the max and the mins, all they're asking you is to compare the vertexes or the vertices. So you would just want to find the vertex on each one. Okay. Let's take a look at problem 2. Now we're going to have to kind of think through problem 3. So as I read it, just kind of try to picture it in your mind. Campers at an aerospace camp launch rockets on the last day of camp. The path of the rocket 1 is modeled by the equation. So for rocket 1, they give us an equation. All right. And the equation is h equals -16t squared plus 150t plus 1, where t is the time in seconds and h is the distance from the ground. The path of rocket 2 is modeled by the graph at the right. So here's your graph over here for rocket number 2. Which rocket flew higher? Very quickly, let me explain to you for any of you continuing on to physics someday. You see that -16? That's the pull of gravity. You see that positive 150? That's the initial velocity of the rocket. And you see that plus 1 at the back? That means the rocket, when it took off, was 1 foot off the ground when it started. All right, and that's just going to intro you into physics someday. But let's keep talking. So rocket 1, we have an equation. Rocket 2, they give us this graph. So don't think that the graph and the equation are the same thing. Rocket 1, they give us an equation. Rocket 2, they give us a graph. So they want to know which one flew higher. In other words, when they ask us which one flew higher, they're asking us about the maximums of each of them. So they're asking about the maximums of both of them. They're asking about the vertex of both of them. Let's take a look at the first one. -16t squared plus 150t plus 1. You guys should know how to find the maximum on this. In order to find the maximum, you simply find the vertex. Okay? Now this is in standard form. Okay. Now how do you find the vertex in standard form? You write x equals, well in this case, x is a t, so t equals, or time equals, -b over 2 times a. So negative b would be -150 over 2 times a is -16. Okay, you plunk that into your calculator and you need to get a solution. So -150 divided by the quantity of 2 times -16, and your quantity. If you guys don't put 2 times -16 in parentheses, you're going to get the wrong answer. All right, so about approximately 4.7 seconds. Okay, so I'll say it's approximate to 4.7 seconds. That's time. That's why I put seconds on there. Now, that is not the maximum. That is when the maximum happens. All right, let's continue on. So if you plug that in, okay, if you plug that in, you will get -16 times 4.7 quantity squared plus 150 times 4.7 quantity squared plus 1. All right, let's go ahead and plug that in. -16 times 4.7 quantity squared plus 150 times 4.7 plus 1 at the end. So I get a height of 352 if we round, 6 feet, and that is the max. Again, this is going to be fairly approximate, so I'll write my approximate symbols. When I plugged it in, I got 352.6 feet, and that is the maximum that the rocket traveled. So as the rocket goes up and it comes back down, there you go. If you're a visual learner like me, the rocket goes up, it comes back down. That is the maximum. All right, let's take a look at rocket 2. Now, there's no specific example for rocket 2, but we can see by just looking at the graph that it happens at like 6 seconds, right? So this spot here That spot up there is your vertex. It's the maximum. So we can notice that it's pretty gosh darn close to 600. So we can say that the max on this one is close to 600. So if we take a look at our question, it says which one flew higher? Clearly, if this one was only at 350 and this one's at 600, we can say rocket 2 definitely went higher. All right, and got it number 2. It says which one stayed in the air longer? Now a drawing is very helpful for me, so we're going to go ahead and do that and take a look at the drawings. Now the good news is rocket 2 already has a drawing for us, and rocket 1's over here. So what I'm going to do is I'm going to, for part A, just draw a real quick sketch of both of them. Rocket 1 and rocket 2. Okay. So rocket 1, it told us, obviously it started like at 1 foot, but then it went up and it reached its max and it came back down at some point in time and hit the ground at a foot lower. Now, something important to realize is that the maximum happened at 4.7 seconds. Now, if the maximum happened at 4.7 seconds, think about what that means, guys. It's going to take another 4.7 seconds for it to hit the ground because it's only halfway through. So this area right here is going to be 2 4.7s because it's 4.7 to get to the highest and about 4.7 to come back down. Okay, now how else could you do this? You could plug in 0 for y, okay? But I'm just going to kind of eye it up and double that. I'm going to get about 9.4 seconds. Now remember, this is just kind of a very rough guess. But if we look at rocket 2 up here, rocket 2 goes up and comes back down. Look at how it takes 12 seconds. And see up here how it says 12 seconds until it reaches the ground again? So if it says which one stayed in the air longer, rocket 2 stays in the air longer because it doesn't come back down until 12. Now how could you do this like actually mathematically for part A? You could plug in 0 for y and solve, or you can just kind of eye it up, okay? But it's good to know that you have options. This would be the more mathematically exact answer, but we can clearly use this answer to let us know that rocket 2 stayed in the air longer. Part B says, what is the reasonable domain and range for each quadratic model? Okay, so let's take a look at part B. Let's talk about the domain and the range for rocket 1 and rocket 2. All right, now this is the only time that your domain is not going to be negative infinity to 0, or negative infinity to positive infinity. Your domain, in this particular example, is your time. So let's think logically. What's the smallest time you can have? 0 seconds. What's the largest time that you can have? When it hits the ground. So right around 9.4 seconds. Okay? Your range is where it starts, or what's the lowest value that it ever goes to. Well, since it's like the height of the rocket, the smallest it can ever be is when it lands on the ground at 0, and the highest it can ever be is what we got up here, 352.6. Rocket 2, the domain again is the time. Make a nice little chart here. The domain again is the time. So, yeah, time's not going to get any smaller than 0, and this one takes 12 seconds to hit the ground. The range again is the height. So you had to think logistically. What's the smallest the height can ever be? Well, when it hits the ground, it's 0. And what did we estimate the max to be? Let's go ahead and estimate this max up here. I'm going to have to say around 575. But again, that's an estimated value. Okay? That's all you have to do for problem 2.